This is our formal lab. We designed an experiment to look at how a change in height, in initial height, affects the energy of the ball when it's bouncing off a surface. The only thing within the system boundary is the ball. It's a closed system. We're looking at the energy of the ball right before the first and second bounces. The maximum kinetic energy is calculated at the last instantaneous point before contact with the ground. Our independent variable is the initial height, and we're measuring the energy of the system. We're looking at the potential and kinetic energy equations. Our method is to drop a ball from the different initial heights and track the position and velocity to calculate the energy. From the initial drop to just before the second bounce, we hypothesized that a drop from a higher initial height would be an overall larger energy. We assumed air resistance is negligible, but if that was included, it would be shown through loss of energy before any bounce. This is just our system schema.
And here is a screenshot of our tracker window. Then we also included the graphs from our tracker data, one for each of our heights. The position and velocity graphs look as expected, with the position graph being half a parabola for the first before bounce 1 and a whole parabola for before bounce 2. And then the velocity graph for both is a line with a negative slope. The acceleration graphs look pretty funky, but if you take a line of best fit, you would see the expected horizontal line there. And then as the height of the ball increases, so does the y component of position and velocity, but the acceleration graphs stay approximately the same. And then this is our table of data with the drop height, bounce height, the velocities before the bounces, and then the instantaneous kinetic energies before each bounce.
So this is just a fundamental representation, physics representation of what's happening to the energy of the ball as it falls. So at the start, all the energy is stored as potential energy between the ball and the earth in gravity. Then right before it hits the ground, the instantaneous moment, all of its energy is kinetic, and that should be roughly equivalent to the potential energy. And then as it bounces up again, after contact, a little bit of energy is lost to that contact, but it makes that bounce. It's still 100% kinetic and slowly goes back to the potential energy as it goes up the bounce. And then as it starts the next bounce, it's 100% potential until, again, 100% kinetic at the bottom of the bounce. The mathematical representation of this is just we had to track the energy. So we use the track total energy of the system. We have EK plus EP equals EI. We track kinetic energy by looking at the final velocity before contact with the ground and multiplying by the mass of 2.7 grams of the ping pong ball. And the potential energy was just our starting height times acceleration due to gravity and the mass of the ball again. Here's a representation of motion again through motion maps. As you can see towards the end of each trial, as the lines at the end get bigger, indicating a greater total energy of the system due to larger kinetic energy. And again, these are just energy pie graphs representing changes in the energy in the system. You can see at the bounce at where 2 is labeled, that is where some energy is lost due to contact.
All right, so possible sources of error were camera angle, unintended force, video frames, so hardware and software issues. And this is how we attempted to minimize that error through various techniques. And for quantitative error, we calculated the expected error value from finding the average error and dividing that from the expected acceleration due to gravity.
For our quantitative conclusions, the total energy of the system right before the first bounce increased linearly by an average of 54.2 grams times inches squared over seconds squared, as the initial height of the ball increased by 3 inches, and this indicates direct proportionality. And this the same principle applies for the total energy of the system before the second bounce, except that in this case, it increased linearly by an average of 35.47 grams times inches squared over seconds squared. Then our qualitative conclusions, a greater initial height of the ball resulted in a greater kinetic energy of the system before the first bounce and second bounce respectively. And then since the total energy of the system before the bounces, each of the bounces is equal to the kinetic energy of the system at those points, we can also conclude that a greater initial height of the ball resulted in a greater total energy of the system before each of the bounces.